we're going to talk about continuity and atomism in ancient physics. So what that means is that we are going to have a look at two very different theories about the structure of reality. Basically, the question that we are going to ask is there something like ultimate building blocks of reality? Is matter composed of something like some indivisible ultimate components that look a bit like the Lego blocks, or is it something more like Play-Doh, something that is homogeneous and full, and that you can keep dividing and dividing and dividing, and you'll always find something that is structurally exactly identical to the thing that you started from? So is reality composed by atoms, or is it a continuum, a homogeneous boom of stuff? That I think is like today we would definitely consider this question as pertaining to physics. So that is what we would say a very scientific question. And we would approach it with a very scientific methodology that is structured in very specific ways and that relies on a mixture of like theory and theory building and experiments and observations of reality. But we're not going to talk about what we think today. We're going to talk about this question as it was approached in ancient Greek, in the ancient Greek context. So in a context in which the boundaries between philosophy and physics were not really well defined. And so something that is interesting, I think, is to see how this question that we would deem very scientific today is approached with tools that we might think are not scientific or that have something that is more similar to, that is actually something that we would call philosophy, probably. So as I was saying, the question is, what is reality really like? What is the deep structure of reality? And there are these there are many different answers that can be given to this question. And today we're going to look only at two that I think are the most famous or the most obvious also today. That I was saying the atomistic option, in which we have little building blocks, and the continuous option, in which we have infinite divisibility throughout, always finding the same kind of thing without bottom. And in the context of ancient Greek philosophy, we have two main schools that we can associate with these two options. On the one hand, we have the ancient atomists, in particular Leucippus and Democritus, that are like slightly mysterious figures in the sense that we know their names, very famous, but we don't know much about them. Leucippus, we really don't know anything about him. We don't even know if he actually existed. Democritus, we're a little bit more sure about his existence, but still we don't have many texts. So we only have reports of what people tell us that he thought. And on the other hand, we have Aristotle. Aristotle, much more well-known figure, one of the big philosophers of Greek antiquity, of whom we have many texts. And in particular, we have his physics. So we have the full theory. So why is it interesting to look in particular at these two figures or these two schools? Well, if we think about the question today, and we ask, okay, what does reality really look like? Are there atoms? Well, the answer, I think, is yeah. Today, we would definitely lean towards the atomistic option. Then it's very much still in question what the atoms look like, what level really is the ultimate level. So atoms, we think, can further analyze into components, but still, we might wonder whether like they're really particles or not. But the idea that a reality is structured in different way at different levels and that there is one ultimate level, whatever that is something that we are very much attached to. What is interesting when we look at the Greek context is that historically speaking, that went the other way around. So in the debate between the ancient atomists and Aristotle, Aristotle definitely won. And Aristotle had a theory that was very much based on the idea that matter, space, and time are all continuous. So you can keep dividing ad infinitum without ever reaching the end. So here you can see a better representation of Aristotle, one in which it looks a little bit more good looking and a bit smug because he made it. And he really won. In historical terms, it's really interesting because at least in Europe, Aristotle's theory remained the theory throughout all the Middle Ages and up until the 17th century. So the idea that matter is continuous and that there are no atoms really was the scientific theory of matter for a very, very long time. And in the 17th century, when the atomistic theory was revived, well, that was in direct opposition to Aristotle. And the 17th century atomists referred back to Democritus and Leucippus explicitly, saying, okay, these guys were right and Aristotle got it wrong. There was a problem. We made a mistake that we have to rectify. And after that, in one way or the other, the atomistic theory remained predominant. So something that is interesting, I think, is to try and look at the debate as it really structured in ancient times to try to understand why that happened. Why is it that Aristotle's continuous theory was more successful in ancient Greece, even if we now think that it's completely mistaken? And another question that I think is linked to that is, were they really talking about the same thing? Are we really engaged in the same debate and we just think that Aristotle got it wrong? Or did something change throughout the centuries and maybe we're not really speaking precisely about the same thing? And in so doing, I think we might find an occasion to think about the interaction between physics, philosophy, and mathematics, and how our presuppositions about how these disciplines should look like influence the content of our theories. Okay, so that was to explain a little bit what we're doing and why, but we can start from looking at the main claims that were put forward by ancient atomism. So I'm just going to talk about ancient atomism without trying to make a difference between Leucippus and Democritus, because as I was saying, there are so many questions about who they were, especially who Leucippus was in terms of historical figures, that it's slightly complicated to try to disentangle them. But for sure, however that happened, there was a resulting theory that was more or less unified that we can label ancient atomism. The main tenet of ancient atomism is very simple, and it's that all that there is atoms and void. What really exists is just two things, atoms on the one hand and void on the other. Atom is a Greek word, and it literally means indivisible. So it comes from the Greek word temnein, that means to cut something, to divide it, and the alpha privative at the beginning, that means that you cannot cut, is what that thing cannot be cut. And atoms are called like that precisely because the idea is that if you have a chunk of matter and you divide it, you divide, but at some point you have to stop because you reach something that cannot be divided, and that is your ultimate component of reality. Atoms are indivisible, but they're also indestructible and ungenerated, so they are eternal, cannot be changed, cannot be divided, cannot be destroyed in any way. They are also invisible. Unclear why precisely, but probably because they're too small. The idea is precisely that they are the deep component, like the underlying components of reality. So we don't see atoms. It never happens to us that we reach something that is indivisible. But we know that there must be something like that. Why? Because otherwise nothing makes sense. So the idea is that the atomists posit the existence of these things that are invisible and like unperceptible, not perceptible in any way, because they are required by their theory to explain the phenomena. The idea is that everything that we see, everything that we perceive in our macroscopic, normal, everyday life is just a derivative aspect. And it can really be just referred back or explained in terms of different compositions of different numbers of atoms. The atoms move in the void, they combine in different ways, and out of that combination result all the things that we see in the world. Atoms can have different shape, different order, and different position, and they can also have different sizes. But apart from that, everything else, all the phenomena that we see are just results. They're just epiphenomena of these combinations of atoms. And here you have a quote: by convention sweet and by convention bitter, by convention hot, by convention cold, by convention color, but in reality, atoms and void. This is a quote that we have a direct quote from Democritus, probably, we hope. What really exists is just atoms and void. And as I was saying, atoms and void are posited even if we never perceive them. They are posited to account for the phenomena. So that looks like a very scientific move that is very similar to what we do in contemporary science. But what are the phenomena that the atomists wanted to account for? What are they interested in? When we say today that we posit some invisible entities to account for the phenomena, we mean the results of some specific experiment. That is not really what happened with the atomists. They were talking about, in much more general terms, about the possibility of experience, of everyday experience, the possibility of things being more or less how we think that they are. Why should they be worried about that? Well, they work in a context in which there had just been something really revolutionary that we can label the Eleatic challenge. So this guy arrived, Parmenides of Elea. He, again, we don't really know much about him, but we know that he had a massive influence in the development of philosophy of the time. Parmenides wrote a poem that is also interesting when you think of the difference between contemporary science and ancient science. He wrote a poem that is metaphysical and cosmological, and it is traditionally referred to by its conventional title on nature. And Parmenides starts from something that sounds very innocuous. He starts by saying what is, and what is not, is not. Now, that might seem mysterious. You might wonder, why would everybody want to say that? But that doesn't sound false. It sounds pretty okay, pretty tautological, pretty reasonable to say that what is, and what is not, is not. However, from this apparently innocuous posit and starting point, Parmenides derives some very worrying consequences. In particular, he denies the possibility of plurality and denies the possibility of change. How did he do that? Well, to go into the details would take a little bit of time, so I'll give you just the very short story. But the idea is that, according to Parmenides, plurality, so the possibility of having many things, requires some sort of intermixing of commission between being and not being. Because if you are something, you cannot be something else. In order for there to be two things, like if we have these two pencils, for this pencil to be different from this other pencil, well, that means that it is not the other pencil. It is itself, and it's not something else. And according to Parmenides, this brings chaos into the picture, we have this commission between being and not being that is forbidden. In the same way, change is equally deemed to be impossible, because in order to change into something different from what you are, there needs to be some sort of interaction between being and not being. If something is white and then becomes red, well, something that was not red becomes red. Something that is white then is not white anymore. Being and not being become intertwined in this very inadmissible way. So this sounds a bit crazy. And of course, there were quite a lot of reactions to that. But he also had some disciples, and you might have heard of Zeno of Elea and Zeno's paradoxes. The most famous one is the Achilles and the tortoise, and we'll talk about it a little bit later on. But Zeno is probably a disciple of Parmenides, and he devises paradoxes that are aimed to defend his master and to support the idea that plurality and change really cannot happen. They cannot exist. And the way in which he argues is by basically it starts by accepting that plurality and change, like that denying the possibility of plurality and change might seem paradoxical. But look, if you accept that plurality and change exist, you end up having problems and paradoxes that are even worse than the ones that Parmenides, than these seemingly paradoxical ideas. Something that I want to flag is that some of the, so we are going to look at a couple of the paradoxes now. Today, most of them are considered mathematical paradoxes, and they are given a mathematical solution. The solutions that we are going to see today are strikingly not mathematical at all. They're completely philosophical, completely theoretical solutions. So again, we see here a different approach to the boundaries between the disciplines. So as I was saying, the most famous paradox is the one of the Achilles and the tortoise, but the one that we are going to start from can be called the paradox of complete divisibility. Zeno starts from supposing that we have one body. And suppose that that body is divisible, and that's infinitely divisible. Well, if something is infinitely divisible, that means that you can divide it. Otherwise, it wouldn't be divisible. But if you can divide it, well, we can suppose that that infinite division has somehow been completed. But if we suppose that an infinite division has been completed, we can also ask what is left after the division. So if to understand what's happening, we can take a simpler case. We can start by a dichotomy. So suppose that we have a ball of Play-Doh and we divide it into two. We want to operate a dichotomy. A dichotomy is a division into two parts. The Play-Doh is divisible. We can suppose that the division has been operated, and we can ask what we have at the end. And if we were talking about the dichotomy, the answer is two chunks. Great. But if we try to do that same thing with an infinite division, we end up having problems, because it seems that that operation, well, we really don't know what we could be left with. Because if we are left with extended parts, like in the case of the dichotomy, well, if we have chunks of matter that are extended and identical to the things that we had at the beginning, well, those are still divisible. So we have not completed the division. In fact, we should go on. Okay, so that's not a great answer. Maybe we are left with nothing. But if we are left with nothing, well, how did that happen? That means that we can't go back to the situation that we had at the beginning. We cannot take the pieces and put them back together. And we have to suppose that something simply disappeared into nothing. That seems counterintuitive. So the other option is that we are left with parts that are not extended, so that they don't have any dimension, they don't have any size, they're like points. But again, how did that happen? And we cannot go back to the thing that we had at the beginning, because things that have no size and no extension, well, however many you have, it seems very difficult to suppose that you can get something out of this unextended bit. This is an assumption. This is an assumption that is not really defended in the Greek context, but everybody accepts, both like Zeno and the Atomists and Aristotle. And bracket on today, now we reject this assumption. So now we think that we can construct something that is extended out of more than infinitely many unextended points. And again, this is part of the mathematical solution that we give to some of the paradoxes today. But that's not the road that any of the Greeks took. And we can see why. Intuitively, it makes a lot of sense to say that if you have zero and you have zero and you have zero and you have zero, well, you can go on forever, but you're still left with zero. So that option is also not viable. So what do we do? Well, this is the situation that the atomists face. So what the atomists do is saying, okay, that's fine. Not great. So we just have to put an end to it. We just have to assume that, yeah, it was not infinitely divisible. The premise was wrong. So they don't really question the argument at all, but they say that's fine. Obviously, supposing that reality is made of something that you can continue dividing doesn't make sense. And so we just have to assume that there are some building blocks. At some point, for some reason, you have to stop dividing. That's it. Another thing that the atomists are ready to follow the Eleatists on is about what is needed for the possibility of motion. So this is a bit of a, like, it's worded in a weird way because it's a direct quotation from Aristotle. But it might be interesting to have a look at it. And Aristotle writes, talking about the atomists. Leucippus, however, thought that he had a theory which harmonized with sense perception and would not abolish either coming to be and passing away, or motion and the multiplicity of things. So here we see that, according to Aristotle, the atomists really were concerned with finding a solution that would save the possibility of everyday phenomena. Making these concessions to the phenomena and conceding to the monist, that is Parmenides and Zeno and Melissus, that there could be no motion without a void, it states that void is non-being, and no part is what is not being. For what is, in the strict sense of the term, is an absolute plenum. This plenum, however, is not one. On the contrary, it is a many infinite in number and invisible, owing to the minuteness of their bulk. The many move in the void, for there is a void, and by coming together, they produce coming to be, while by separating, they produce passing away. So here we see that, like, according to this narrative by Aristotle, the need for positing atoms and void comes from having to solve these paradoxes and having to, like, block this very weird logical argument that led Parmenides to deny the possibility of plurality and of motion. And the way in which they do it is basically, like, that's very elegant, because with one move, they manage to solve all the problems. They posit an infinite number of indivisible bits that are dispersed into void. And in so doing, they can solve everything at the same time. because the atoms are indivisible, they block the paradox of divisibility, and because there is void, they allow for the possibility of motion. And sorry, because there is void, they allow for the possibility of motion, and void also allows for plurality in the sense that because two atoms are divided by void, they are recognizable as two different things. So that's brilliant. The only thing is that it requires positing the existence of void, that is, the existence of something that is nothing. And that is slightly paradoxical. And they don't really have any specific theory of what void is, nor any experiment, nor like it's just all on the basis of this very logical reasoning. So before moving on to Aristotle, just another couple of things about how precisely the atomists thought about the atoms. And again, here we have another quote by Aristotle that really stresses that the atomists are responding to the Eleatics and they are following their argument, and that the need for positing the existence of these indivisible atoms comes from having to face their paradoxes. So here, the argument of the dichotomy is the argument of this infinite divisibility that I spoke about. So the idea of indivisible magnitudes really accepts the fact that what is one and indivisible. It just multiplies it. Each atom is a little bit like that unitary entity that was posited by Parmenides. And it's just the existence of void that allows them to be plural, to be more than one. And by having these two levels, the atomists can say that macroscopic bodies are divisible without really having to accept the divisibility of matter itself, because bodies are not really divisible. Like, in a way, they were already divided. In a way, when we divide a macroscopic body, we are not cutting up something that was previously one, but we are simply disassembling something that was already structured in bits and pieces that were divided since the very beginning. Since, like, really, really the beginning, because atoms are eternal. So they have never been different from themselves. Now, this is really, this whole packet is taken directly from Parmenides. So the atomists really do not reject Parmenides' own interpretation. They basically multiply it. They twist it by allowing for the existence of void, and they find a way around the argument. So here in this slide, we have a quote by Parmenides himself from the poem on nature, and where Parmenides is describing this one thing that he thinks is reality. And he says, what is now altogether one and continuous. It is not divisible, since it is all alike, nor is there any more or less of it in one place, which might prevent it from holding together, but all is full of what is. So I put this quote here because I want to talk about what it means to divide something, and why is that problematic. Parmenides starts from the assumption that we have in front of us something that is one and continuous, that is to say, something that is homogeneous, that has no internal differences. Now, what's the problem there? That if something is homogeneous, so all alike, all of its parts are identical to the other parts, why should we be able to divide it in one place rather than in another place? There's nothing in the object itself that requires us to divide here and not there. This I wanted to flag because that's an argument that is really powerful, and that's something that the atomists really build all their theory on. And that's something that we still use very much in philosophy, and that's called now the principle of sufficient reason. So in order for the division to be possible here and not there, there must be a reason. If the two positions are identical, well, there is no reason why you should be able to do something here and not there. But that's very dangerous, because as soon as you allow that something homogeneous is divided anywhere, well, then it is divisible everywhere. And if it is divisible everywhere, then it is infinitely divisible, but that opens up chaos. And so that's why the atomists were like, okay, no, not divisible. Forget it, not divisible at all. So we have this very strict connection between homogeneity and indivisibility, both in Parmenides and in the atomists. Now, what are the problems with that? Like, it seems that, okay, it might be a little bit weird. We have these things that are invisible and unobservable, posited by reason, but that seems to work. And when if we are just thinking about the structure of matter, it does work, but it doesn't really solve all of the paradoxes that Zeno has. In particular, it does not solve any of the paradoxes of motion. And that's because, again, like the atomists were worried with the possibility of motion, but they were just happy to say, oh, there's void, so the atoms have some space where to go. That's fine. They don't have a theory of motion. And that again strikes us a bit if we come from a scientific perspective, because in order to say that motion is possible, you can't just say, yeah, things have somewhere to go. You have to explain how the motion works. But the atomists don't have that. They don't have a kinematic theory. So this is one of the most famous paradoxes of motion, like one of Zeno's paradoxes of motion. And you can give many versions of it. The idea is that if the distance between 2 points is infinitely divisible, then motion is impossible. Why? If you suppose that Mary wants to catch the bus, she's late, she sees the bus coming, she wants to run to the bus stop in order to catch the bus. Well, Mary is here, the bus stop is at distance 1. Before getting to the bus, Mary has to cover half of the distance. So she has to get halfway through. But before getting halfway through, she has to cover a quarter of the distance. And before being able to cover a quarter of the distance, she has to cover 1/8 of the distance, etc., etc., etc. So Mary cannot even start running towards the bus, because before any step, she should have taken a smaller previous step. There are 2 versions. You can do this as Mary cannot start or as Mary cannot reach the bus, but the structure is identical. Another version, another paradox that points to similar difficulties is the Achilles. The Achilles is paradoxical because it says, well, in a competition, Achilles, the fastest man on earth, could never reach a very slow tortoise, because whenever Achilles arrives, if they start at the same time, in the time that Achilles took to arrive where the tortoise started from, the tortoise will have taken a little bit of a step, an extra step. So here we have Achilles and the tortoise at the beginning. Then at time t1, Achilles is where the tortoise started from, but the tortoise is not there anymore. Okay, fine. Achilles can cover that distance, but in that time, the tortoise will have proceeded another little bit. The distance between Achilles and the tortoise becomes smaller and smaller, but Achilles can never reach the tortoise if time and distance are both infinitely divisible. So you can see that here, with respect to the problem of the dichotomy, we have an extra difficulty. While with the infinite divisibility stuff, we were just talking about the divisibility of matter. Here we're also talking about the divisibility of distance and of time. And all these things are things that the atomists didn't really care about. If they did, we don't have that bit of the theory. But they didn't have a theory of motion, and they didn't have a theory of spatial distance and time. Aristotle was really not happy with that, and he built a completely different picture of reality on the assumption that it's important to have a kinematic theory. So it's important to have a theory that accounts for the possibility of motion in full terms. That void doesn't really make any sense. Like, what is void? It's unclear. And that positing indivisible atoms, well, that might be cool, but that raises a lot of problems. And in particular, it raises some problems for mathematics. And here again, think about what it means to have this interconnection between physics and mathematics. According to Aristotle, if there were atomic atoms, well, that would have meant that indivisible magnitudes would all be commensurable, and that would go against Pythagoras' theorem. So geometry, Euclidean geometry, like the normal geometry that we study, is all built on the assumption that magnitudes are continuous and that there is no smaller one. You can always take a smaller one. So in so doing, in trying to keep all these pieces together, Aristotle does something that is incredibly sophisticated, and he comes up with the first theory of continuity. So as we saw already, he is not the first one to talk about continuity at all. Parmenides spoke about continuity, the atomists speak about continuity, but they simply say what is continuous is homogeneous and indivisible. Aristotle flips this, and it really says that what is continuous is actually infinitely divisible, as long as we understand infinite divisibility in the right way. How? Well, if we think about the dichotomy, we can about this paradox of Mary not being able to reach the bus. Well, Aristotle notices something that is quite important. There's some sort of ambiguity when we say that before getting to the bus, Mary needs to get halfway through. There's a sense in which this is obvious. So in order to get to the bus, Mary needs to go through all the positions that are in between. So she needs to, at some point, pass over the halfway point, the midpoint. But she doesn't necessarily, but that doesn't seem to be a problem. What is a problem is if Mary stops there. So I'm now trying to make that a little bit clearer. I'll briefly read the way in which Aristotle puts this, even if it's slightly obscure. But he says, therefore, to the question whether it is possible to pass through an infinite number of units, either of time or of distance, we must reply that in a sense it is, and in a sense it is not. If the units are actual, it is not possible. If they are potential, it is possible. For in the course of a continuous motion, the traveler has traversed an infinite number of units in an accidental sense, but not in an unqualified sense. For though it is an accidental characteristic of the distance to be an infinite number of out distances, it is different in essence and being. So the second part is like really draws on Aristotle's theory of like accidents and essences. That's not super important. But the first part, this difference between potential and actual, that's where the key magic happens. And like the core idea is that Aristotle distinguishes between a continuous line and a divided line, a continuous distance and a divided distance. A continuous distance is one and unitary, and it is divisible, but it's not divided. And that's a pretty important thing. While if you do divide it, then it is actually divided, not just potentially divided. So it's not just divisible. It's not just that you can divide it, but it has been, in fact, divided. But in order to pass from the one to the other one, like from the one to the second, from a potential division and an actual division, something needs to happen. In particular, if we're talking about Mary running to the bus, in order for the distance to be divided, Mary needs to stop at some point. But if Mary does want to get to the end, and she does want to get the bus, she better not stop. And if she doesn't stop, according to Aristotle, the situation is pretty clear. She's not doing anything else than just running one distance altogether. There are no infinitely many anythings. We could, if we wanted, divide that distance into infinitely many bits, but Mary is not doing it. And so there's no paradox. So in a way, according to Aristotle, Zeno does identify an impossibility, but that impossibility is not the way in which we do things. We do not try to go through infinitely many steps, and we don't have to. And here, to very briefly bring this back to the issue of the composition of matter, well, remember that the atomist said that if a homogeneous magnitude is divisible somewhere, then it is divisible anywhere. And they were worried that that would bring to paradoxes, because then you have anywhere, then everywhere, then infinitely many, then disaster. Aristotle simply says that if something is divisible somewhere, then it is divisible anywhere, but not everywhere at the same time. At any point, you can divide, but if you divide here, you're not at the same time dividing anywhere else. The division, like, the choice is absolutely random, very open, but you can't do both at the same time. You have to pick the one or the other. So at every point, it is possible that an infinite magnitude is divided, but it's not possible that it is divided everywhere at the same time. What that means is that the division is infinite in the sense that it can go on forever. But if it can go on forever, you can never finish it. And so you never have the problem of what you have when you have finished, precisely because you can never finish. And something else that I wanted to very briefly mention, and then I'll close, is that in so doing, Aristotle gives a theory of continuity that is extremely powerful, and that like introduces a connection between physical properties and mathematical properties. So we have this idea of divisibility, the infinite, those are all mathematical properties that have to do with the physical reality, that are used to explain physical reality. And then it's not just a theory of matter, but it is at the same time a theory of motion, space, and time. And so we have all these physical magnitudes that are required to give a scientific account of motion that are brought together. And because, according to Aristotle, they all share the same structure, we can compare them and we can build a theory that draws on all of them rather than having different discourses. And in particular, they can all be modeled by the geometrical line. And that's something that we still do. We still use a line to, when we do physics, to model time and to model space. So these are all things that we are kind of like, we have inherited from an Aristotelian way of looking at the world. So when after the Middle Ages, modern atomists rebel against Aristotle, that's obviously an extremely powerful and very important move, because like the influence of Aristotelianism was kind of blocking science in many ways, but it's not a going back to what the ancient atomists were doing. It's some sort of like going forward, keeping something of both theories. And I think that that's quite interesting, and that it might be useful to look at what is it that we have inherited from both these traditions.